In this, our final lecture on nanotechnology, I'd like to begin with a discussion of some exciting topics, some of which are a little less explored as those that we've covered throughout the course. And then I'd like to see how we can pull it all together. We can look at the history of nanotechnology till today and think about the future going forward. Let me start in on the first of one of a number of exciting topics that we haven't gotten to spend too much time on. In a way, what I'm going to describe is kind of an integration problem. The idea, it's sometimes called smart dust, and the idea is one where sensors could be everywhere. Sensors that we desire to measure properties of our environment, to monitor a vulnerable environmental enclave. There are military applications in which we would like to be able to send tetherless sensors into an environment to monitor what's going on there. The reason I call this an integration problem is because we have all of the building blocks in place already for this. We've talked in this course about methods of sensing, like optical detection, our ability to make cameras that are incredibly small, lightweight, low in cost, low in their power consumption. We've also talked in Shana's discussions about biosensors. We're able to detect biomolecules or chemicals in the environment. This is very relevant to industrial sensing or to learning information about our biological environment. We know that we're able to communicate information at vast information rates using the transceivers that are inside our cell phones, and we're able to do so in a very manageable way. And so building these sensor networks based on ubiquitous small sensing devices that are so low in cost you can imagine just kind of letting a powder puff of them into the air and having them land in the environment is something that in principle we should be able to do. Now, there's that integration problem of putting together the storage of energy. In fact, we're going to want to harvest energy from our environment. We may do so photovoltaically. There's also ways to scavenge mechanical energy, vibrations, or thermal energy, changes in temperature from one region to another, and to use these to scavenge a little bit of energy from our environment, store it up, and use it in powering our remote sensor, sometimes called a mote. The communications, as I said, is something we can take care of, but how about the networking side of it? When we launch a bunch of these little sensors into a region that we're interested in monitoring, how are we going to ensure that they can all communicate back to us, to some kind of base station? Well, one of the ideas is the formation of what are called ad hoc networks, spontaneous networks, where wherever these little bits of smart dust land, they're able to talk with one another. Because they're close to each other, the amount of power they need to communicate with each other is very small, and then they can gradually relay the information back to a central point. So these are also smart network or intelligent networks that can figure out how to form and propagate information in the most energy efficient manner. Here's a couple of pictures of some of the early prototypes. They're kind of millimeters in size, and they're very compact as a result. And there's a whole lot of functions that can now be integrated into them. The applications I mentioned already were some military applications prospectively, espionage, you can easily imagine, environmental sensing. But there's another application area that's a very interesting one for these sensors, and we touched on it just a little bit when we were talking about power and energy. We were talking about the smart grid. There we were talking about how when we bring renewables such as solar energy, wind energy online, that we can be pushing energy in either direction, from the direction of production to consumption, or now vice versa, that each of us can become an energy producer. But one of the key components of a smart electrical grid, one which is robust, which can accommodate renewables, which doesn't have to throw away some sources of energy simply because they can't be accommodated, which negotiates across the grid. One of the components of this will be effective sensing of the electrical properties of power that's conveyed or delivered to that grid, and then kind of a synchronization, a management across that grid of the waves of energy that are being conveyed. And so here again, these sensors that are very low in cost, ubiquitous, robust, very good at communicating, and where when we introduce somebody new onto the grid, they can rapidly become part of that network, kind of an ad hoc version of network formation. All of these concepts apply as well there in the realization of one of these intelligent energy grids. Another topic that's seen great attention, really captures people's imagination, is referred to as cloaks of invisibility. And in fact, cloaks of invisibility are just an example of one of the exciting application areas for new materials that are referred to as metamaterials. And when we shrink them down, they become nanomaterials. But they're interesting not just at the nanoscale, but also at larger length scales. Let's talk a bit about these metamaterials and how they relate to cloaks of invisibility. Here's the idea that we can wrap an object that we wish to cloak in a material that essentially ensures that electromagnetic waves, such as light or also microwaves, will pass around it and then recombine as if the object was not there. So normally, if you were to have an object and it would see a light impinging upon it, or say a microwave frequency radiation impinging upon it, then that object would alter both at the source, so in the reflection, and also in transmission on the far side of the object. That object would alter what happened to those wave fronts. They would become, instead of being planar and flat, they would become rippled. It would be like how in an ocean with waves lapping up on shore, if you were to stick a buoy there, the buoy would alter how the waves formed in the longitudinal direction. And so waves, therefore, when they're interfered with in this fashion, render the objects that interfere with them detectable. So this is, of course, how we experience light and how it's transmitted or not transmitted through objects and how we see objects in our way. Now, the idea with these metamaterials is that instead, we're able to surround an object with a cloak that ensures that the waves pass around it and then recombine as if the object was not there. Now, to make something truly invisible, what are you actually going to want to do? Well, first of all, if you're thinking in the optical wavelengths that we see with our own eyes, clearly all the colors of the spectrum, you're going to want them all to manifest this property of being not disrupted by the object. Another is that you're going to want to ensure that not only does the shape of the waves, the optical waves that makes it around this object, combine and keep its structure and not be perturbed, we're also going to want to ensure there's no absorption. Metamaterials have made a progress in this direction. By metamaterials, what we mean is artificial materials, entities where instead of just using a pure phase of one crystal or one metal or one semiconductor, or one dielectric, a transparent material, we combine these together, often in a periodic structure or a partially periodic structure. And the ways in which electromagnetic waves propagate around them have their dispersion influenced. And by dispersion, a concept that we talked about when we were discussing fiber optic communications, we mean how the behavior of this light depends on its frequency. So these metamaterials had initially been implemented at microwave frequencies. There's now been recent progress in building them and implementing them and utilizing them at optical length scales. But there are two challenges that remain not fully resolved. The first of these is that the way these dispersion properties are engineered, the way the frequency dependence of these behaviors are engineered, ensures that we can mostly do this essentially at a single frequency. So, for example, if you're interested in flying a plane through some airspace and you know what people may be looking at, what frequencies they may be using to look at you, if you can predict that they'll use a particular frequency of the electromagnetic spectrum, then you may be able to cloak relative to that frequency. But if, as when you think of visible wavelength applications in using our own eyes, if you're interested in being able to cloak something across the full visible spectrum, that's going to be much more challenging because these metamaterials are actually using dispersive properties, which are inherently narrowband, in order to guide light around their edges and have it recombine as if it were not disturbed. The other component that makes this metamaterials field and cloaking still challenging is the fact that there still is some loss, some absorption of light that occurs within these materials. And For the moment, then, these remain detectable. Perhaps the shapes of the waves are kept as they were on the front side of the object, but the amplitude of the waves is not perfectly retained. And so there still is a means of detection. It's subtle, but there's a means of detection. So these challenges of bandwidth and loss will need to be addressed, and these are exactly the kinds of questions that researchers are continuing to work on. I wanted to talk about another very exciting area for the world of nanomaterials that has made great progress, but has yet to be fully drawn to a complete conclusion, commercial products generated and things like that. And I'll call this conformable and deformable nanomaterials. Let me describe a bit what I'm talking about. We've talked in this course about how semiconductors such as silicon are so capable in electronics. We've talked about how gallium arsenide is such a good material for light emission. In fact, it happens also to be an extremely good material for making a solar cell out of. We've discussed single-walled and multi-walled carbon nanotubes, which can be coated onto things. We talked about quantum dots. But often, we're interested in integrating multiple functions. We're interested in putting down an electronic device on silicon, combining it with, say, an energy harvesting device, such as one based on gallium arsenide, perhaps making a photodetector out of a third material, putting them all on the same substrate. Well, traditionally, semiconductor processing and growth have worked based on the process known as epitaxy, which we described in the solar lecture, where we were talking about triple junction devices, about growing perfectly lattice-matched crystals on top of one another. But now, this panoply of materials I just described don't even necessarily all have lattices. Some of them could be amorphous, some of them could be crystalline, some of them are of shapes that are even non-planar. And so it's not obvious at all how to use our traditional stacking of crystals on top of each other to build stacked heterostructures or heteromaterials. This is where a professor at University of Illinois at Urbana-Champaign, John Rogers, has made incredible strides and has really captured the world's imagination. Professor Rogers has come up with a number of ways to take really a diverse array of materials and first put them down onto a first template and then use a transfer printing process in order to transfer this layer onto another substrate. And he's able to do this many, many times. He's able to use repeated application of this additive process that use these soft stamps and these donor substrates that donate their materials that we've coated onto them and integrate them onto a stack to make a three-dimensionally structured, heterogeneously integrated material. He's able to combine in this way both rigid and flexible materials and devices. That combination is very powerful. In fact, it's caused a lot of people to question whether the need for nanomaterials for their flexibility alone is required, because what John Rogers has managed to do is integrate rigid materials onto flexible substrates, singulate them appropriately, and have them flex. And so he's shown that there's more than one way to build a flexible material if one uses some flexible thinking in assembling the entire stack of materials. This has a whole diversity of potential application. So one of the things it allows us to do is to combine together devices that look in incredibly different frequency regimes. We're able to take the building blocks of radio frequency electronics, the basis for our cell phones, also the basis for some gigahertz imaging or microwave imaging, and we're able to combine it now with materials that are much better suited to imaging in the optical domain or perhaps in the terahertz domain. It allows us to combine things like carbon nanotubes and carbon nanotube arrays, which have had diverse applications ranging from catalysis, as we discussed together, energy harvesting, but also biological sensing. It's enabling some interesting devices that allow cardiac mapping by integrating electronics and biological materials together. It's potentially leading to some implantable materials, implantable electronic materials that can also be used in medical applications. And so it really is changing the way we think about a world divided into the rigid and the flexible, but instead this strategy finds ways to integrate those things that are traditionally made on rigid substrates and puts them onto flexible substrates. In fact, the concept is potentially also very useful in solar energy harvesting because some of the most promising materials from an efficiency standpoint in solar energy harvesting are based on these more exotic compound semiconductors grown on a costly compound semiconductor substrate. But there's recent indications that we can slough off the upper layer of that compound semiconductor substrate that we've grown towards our photovoltaic purpose and transfer it to a much less expensive substrate and then reuse the costly substrate to grow the next layer, to grow the next device. Now, these conformable or flexible materials, in a way, they're just one example of materials that have shape that's changeable. And one of the more interesting concepts is to have materials having these shapes that are alterable, but where the materials also have a memory. In fact, these shape memory materials, such as shape memory polymers, are able to retain 2 or 3 shapes in their memory. And then we can switch them. We can tune them using temperature or an electric or a magnetic field or even light in order to alter their shape. There's a very practical example of where one would want to do this, such as in the introduction of cardiovascular stents. Here, the stent needs to be small, kind of in its condensed phase as we insert it along a vein or an artery. But then we want to expand it to prop it open and to leave it in place at the appropriate location inside the patient. And so in this case, the concept of using shape memory materials is very attractive, for it allows us to alter from the shape suitable to insertion to the shape which we will want it installed within the patient. We spent a lot of time in this course talking about technology, talking about its potential, talking about applications or anticipated applications of nanotechnology. But it's very important, including in a field like this that's filled with excitement and optimism, to think about the risks, to think about the downside. And there certainly are researchers looking at the environmental implications of nanomaterials. They ask things like, what if there were an unintentional release of certain nanomaterials into the environment? What would their fate be? There's also people who look at questions in ethics of nanotechnology and nanomaterials. Questions such as, how far will our power extend to work at the nanoscale? What new properties might we be able to endow nature with? How do we ensure that we don't cross the boundaries of what's societally appropriate to work with nanotechnology? On the nanomaterials questions, there's been a lot of work looking at the fate of nanoparticles in the environment. Again, what if either deliberately or accidentally certain nanomaterials were introduced into the environment? And the answer is that there are many answers. It depends on the nanomaterials. There are certain nanomaterials that essentially get broken down into the environment the way any number of organic molecules would. There's others that are retained for longer and longer within the environment. And those, of course, are the ones that have then the potential to be taken up as part of an ecosystem and do damage. So there have been studies, for example, on how carbon nanotubes at very elevated concentrations can be dangerous to the health of certain fish and small mammals that have been studied in the context of this research. My own opinion on this work is twofold. First, that it's extremely important for all of us in the field to be participants in these investigations into the fate of nanomaterials in the environment. For those of us who work more on advancing the technology for its own sake towards a particular application, it's tempting to put all our energy just into those questions. But in fact, we need to be part of shaping how the community, the regulatory agencies respond to the emergence of new classes of materials with new properties. I think my other thought is that fundamentally, the issues that are presented from a regulatory and environmental standpoint through nanotechnology, through nanomaterials, the issues are not qualitatively different from the issues that exist across process chemistry, from the creation of new molecules and materials. Like all fields involved in the synthesis of new materials, new molecules, new structures, it's important for nanotechnology to be part of the regulatory process, to be aware of the health implications of the materials that it's generating, and it needs to participate in that dialogue, but that the fundamental nature of the questions that emerge from nanomaterials from a regulatory standpoint, the fundamental nature is not different, but the details are likely to be different. And so we need to be part of that conversation. And we need to look at it early. We can't wait until something's just ready to go into the market in mass production. Now is the time to be participating in that conversation. I'd like to close our course with a couple of reflections back onto the history of the field of nanotechnology, including the early history. And then also think a bit about the directions in which this field can go in the future. And to do this, I'd like to recall a speech that Richard Feynman, professor from Caltech, gave in 1959. The speech was called "There's Plenty of Room at the Bottom, an invitation to enter a new field of physics." In this speech, Dr. Feynman, who wasn't explicitly working in this field, he was a more fundamental theoretical physicist, but he went into some very intriguing speculations about the possibility of working in the scale of the very small. Let me just touch on a couple of things that he mentioned. One was that he felt that going into the regime of the very, very small, where he talks about the bottom, where there's an abundance of room, it's not going to illuminate fundamental physics. In fact, that this fundamental physics, even by that time, was becoming extremely well known. Feynman himself was diving deeper and deeper into the strange particles that make up matter, that constitute the protons and neutrons that constitute matter. So it was in the subatomic world. But he did say that perhaps there's an analogy with solid-state physics, and solid-state physics then was relatively young. And in that it wasn't so much that it would be illuminating the fundamental new concepts of how matter is constituted, but instead that it would provoke great interest into what happens when you combine phenomena in complex fashions. And I think that insight is very real, and in a way, one could consider nanotechnology simply to be the quantitative improvement in our dexterity in manipulating matter and turning it into more and more complex structures. Dr. Feynman also remarked that even though he didn't give too many details of this, which is itself interesting, but he said that he felt that gaining dexterity on the scale of the very small would have a huge number of technological applications. And that I think is hard to argue with. And I think one of the areas in which Dr. Feynman was broadly right, that there would be huge numbers of applications, but one of the areas that was so hard to foresee is what those applications would be. He spoke specifically about manipulating and controlling things on a very small scale. And he predicted that in the year 2000, again, this was 41 years before the year 2000, he said in the year 2000, when they look back at this age, people will wonder why it was not until about 1960 that anybody began seriously to move in this direction. And that itself is an interesting point, that they were, as Dr. Feynman noted at the time, there were a number of capabilities that were just emerging that allowed people to start exploring, manipulating matter at the nanoscale. The transmission electron microscope was already well in place, and people were able to image down to the length scales that we've been looking at together. But primarily they were imaging natural materials, things that had already been made. And one of Dr. Feynman's insights was to say, how can we turn this around and start to engineer on this length scales ourselves? And specifically to that point, he said, why can we not write the entire 24 volumes of the Encyclopedia Britannica on the head of a pin? It sounds like a crazy thing to do, but he did the math and worked out that essentially it would be necessary to reduce the font size by a factor of 25,000. And so those little dots that made up the fine halftone reproductions of images in the Encyclopedia Britannica that were about 1/150th of an inch across, by the time you scaled them down 25,000-fold, they would become about 8 nanometers in diameter. The word nanometer was available then. He used 80 angstroms, which was a more conventional unit for people to use, especially then before people explicitly started talking of nanotechnology. He pointed out that this would be 32 atoms across in a typical material or a metal. And so the dot, if you took its square of that area, would be of the order of about 1,000 atoms. And then he said, well, this is not beyond our capabilities to imagine doing. It hadn't been done yet. People hadn't started writing on this kind of length scale at the time. But he imagined how it could be done. And he essentially said, let's take our electron microscopes and let's turn them into writers rather than just readers. Let's orient our atomic beams and let's carve matter. Let's change the properties of a material using these electron beams. Let's modify it that way. And as a result, we can focus down using the much smaller wavelength of electrons than photons have, and we're able to write. And then, of course, we can essentially use the same instrument in a different mode to read. Well, what's interesting about that remark is that that's precisely how one of the major forms of crafting matter at the nanoscale did emerge. Electron beam lithography, which is one of the ways in which we get beyond the limits of photolithography, the resolution that's available there, the optical resolution, and into the electron resolution scale. That is achieved essentially by reversing the operation of an electron microscope into write mode instead of read mode. Dr. Feynman also talked about the role of DNA, the fact that when we get down to these length scales, and it seems so surprising that one could put all 24 volumes of the Encyclopedia Britannica on the head of a pin, but he then pointed out that DNA already was known to do the same thing, that the amount of information communicated there is very efficient from the point of view of utilization of atoms. So for one bit, one binary piece of information, one only requires about 50 atoms, whereas his modest proposal relied on 1,000 atoms per bit of information. So in that sense, he also anticipated that nanotechnology, as it evolved, would be gaining inspiration from what the biological had done, and that many of our checks or many of our reference points as to the potential of what we were doing would come from the world around us, that there would be proof points through the biological as to what one can do, what kind of control and resolution one can have. Another interesting point that he made is that a lot of the materials that were being worked on then in solid-state physics, they were based on very perfect crystals. They were based on moving towards purity, and so one could achieve control and delocalization of electrons as is achieved in silicon and other semiconductors. But he noted that at the time, they weren't making checkerboards where you might have one material and then a second one and then the first and the second in various complex arrays. Instead, the focus was kind of onto purity rather than onto controlled impurities. But in fact, that notion of a checkerboard is really a description of the way metamaterials work. It involves combining at least two sets of materials, creating what researchers have called binary superlattices, which has now become very much something that researchers focus on in making new functional materials. It's interesting to ask what was not present, what was missing from this view. Well, I would say that Dr. Feynman's view certainly did start, if you like, from the top. He said there's plenty of room at the bottom, but he was starting from the macroscopic and wondering how we could take the Encyclopedia Britannica and write it on the length scale of the nanometer. And while he did certainly touch on DNA, an emergent phenomena, a material where the synthesis occurs starting at the nanometer scale rather than starting at the macroscopic scale, his focus was more on the top down. And that leads to another interesting point that he didn't explicitly anticipate because, of course, the field of electronics was in its early days. In 1959, we didn't have these complex integrated circuits or even precursors to them. We were still at the age of perfecting the discrete transistors that would then be connected together to form electronic integrated circuits. He didn't explicitly anticipate the way in which the field of circuits, the field of electronics would play such a crucial role that in a way the field of photolithography would be writing the Encyclopedia Britannica with almost the resolutions that he anticipated today, down to the sort of tens of nanometers length scale that we're now able to write at. In fact, I think he would have been surprised that we're still using light, shorter and shorter wavelengths of light, but we're still using light to write our smaller and smaller electronic circuits. And this has often been called the surprisingly long longevity of photolithography and how it's extended forward so much. Also, I think interestingly, Feynman didn't explicitly anticipate how the rules of the game would change, that he was entirely aware of quantum effects occurring at the short length scales. This was the area in which he was very much an expert. But I think one of the most exciting things about nanotechnology today is the way in which the rules of physics that we work with, the playground, the grammar in which we build new materials, the rules of the game are altered when we get to these shorter length scales. And finally, I think perhaps the broadest comment, which again, he got right, which was that there would be huge technological implications. But what exactly would they be? That is so hard to anticipate. And so much of what we talked about today has been medical in nature. So much of it has been related to energy. And perhaps this comes in part because, of course, one hadn't explored the nano world in all of its details, but also that societal needs, what people think are important, what politicians think is important, what funding agencies, what peers within the research community decide is important. These are things that influence where the focus is. And so much investment has been made into nanotechnology focused on energy because society has such urgent needs in these regards. Well, with that, I'd like to thank you for your interest in this field. As you can tell, it's one that I'm incredibly excited about. It's one where I think we're full of potential. I think we haven't explored that full potential. And I think just as Feynman wasn't able to anticipate all the areas of application, I don't think we've even scratched the surface of all the implications and applications of working with materials at the nanoscale. I hope that with this introduction, you'll stay tuned, you'll participate, you'll learn as the field evolves, because it's an exciting one. I'm hoping to be along for the ride for quite a while into the future, and I hope that you'll get to partake in it as well. Thank you. We've spoken about capturing energy from the sun. And capturing is the right word for this. Sometimes we talk of energy production, but really we're just harvesting what's being given to us from the sun. But there's another key part of managing energy, especially renewable energy, and that's storing it. In this lecture, we'll talk about how nanotechnology is enabling us to advance and enhance the storage of energy. We'll speak about using nanomaterials to improve the density, measured either by weight or volume or both, by which we can store energy. And we'll also talk about novel concepts, ways of using viruses, for example, to assemble new styles of batteries for us. But first, I'd like to speak just a bit about the balance between harvesting energy and storing it. We anticipate in the future a much larger fraction of our energy budget coming from renewable energies. Solar energy is an example, wind is another good one. And so many attractive things about these: abundant, clean, pollution-free. But one of the challenges that renewable energy forms present is that we don't turn them on and off. They're not what we call dispatchable sources, the way, say, a coal generating station would be, where we can turn up and turn down the amount of energy production at our will. In the case of renewables, solar, for example, a cloud comes by, and the amount of solar energy available to us at that moment changes. Now, that doesn't necessarily map perfectly onto our energy needs. In fact, if you look at the time of day cycles, if you look at the way solar, the sun rises in the morning, and then right at midday we get a great deal of energy, and towards the end of the day less so, and overnight none. This also mandates the need to buffer, kind of hedge these temporal variations in the available amounts of energy. That's kind of a time of day variation perspective. We have some cycles throughout the day where our energy needs vary, kind of along lines with the sun. So, for example, an air conditioner is typically needed more at the peak of the day when the sun is up, and so that's a good alignment. But there are many other reasons why it would be attractive to be able to play back energy at a different time from when it's made available. In fact, a new concept has emerged recently in the management of energy known as the smart grid. The smart grid recognizes that the traditional power distribution network is based kind of on unidirectional flow of energy. It's based on the idea that we have a small number of large centralized power generating stations that spread energy out towards the customer. But with renewables, now the customer for energy, you or I, is also producing energy, say, on our own rooftop. In fact, we may produce sometimes more energy than we need. We may wish to sell our energy to our neighbor or to somebody in another state, another part of the continent. And so now the grid needs to become two-dimensional. We need to be able to buy and sell energy from many, many local points. And one of the key elements in building a better smart grid that's two-dimensional, two-directional, and that allows the flow of energy in a managed fashion without losing control, without leading to blackouts or brownouts, one of the key elements is energy storage. So what that means is that our challenges on the energy storage front occur in many different scales. There's a familiar one, say the battery inside your mobile device or inside your laptop. These are obviously crucially important for a variety of reasons. They enable us to go anywhere, go everywhere with energy, computation, and communications. We've marveled in our discussions of nanoelectronics at the rapidity with which mobile computing has become available. We've marveled at how nanostructured materials, nanoscale transistors, have allowed us to communicate at remarkable rates anywhere. But until now, we haven't marveled at the fact that we're able to take the power with us that we need anywhere. In fact, people often remark at how the computing power that you have in your laptop is vastly, vastly greater than the power in some of the computers that used to fill a room. Well, the same could be said from the power standpoint. We're able to take this power with us anywhere we go, have our battery packs last for 10 hours, enable continued use and enjoyment. So the mobility that batteries and related devices enable is tremendous. But this can also be scaled up. Imagine in the context of the overall energy system, our desire to take large quantities of renewables, say solar energy for a community or on a solar farm, and store that. And that's where batteries can play a role, but fuel cells, which we'll speak about a little bit today, provide another strategy for storing energy. And what they do is they decouple the playback of the energy from the storage of the energy. In a battery, which we'll talk about in a second, the means of energy storage and replay are kind of integrated with one another. But in a fuel cell, we have the fuel, such as hydrogen or ethanol, and separate from that, we have the cell, which takes in that fuel and which spits out energy. And so, depending on the scale we're interested in, depending on the cost, depending on whether portability is a requirement, or whether you're just looking for a stationary and very cost-effective method of energy storage and playback, we're interested in different systems. In fact, there's another exciting technology that we'll also speak about today and that's benefiting from nanotechnology called supercapacitors. And what supercapacitors do is they function kind of like batteries. They're closed systems. They're also self-contained. But they allow us to charge them up much more rapidly and then also play back their energy in much bigger spikes and more rapid spikes. So one of the example areas in which supercapacitors are expected to have a use is in automobiles, where when we start it up, we need a real burst of energy. Typically, that's challenging for a battery to supply. And when we use the brakes and we want to store the energy from some kind of electrical device, a storage device inside our electric vehicle, supercapacitors are able to receive that energy very rapidly and very efficiently. So let's dive into batteries now. These, of course, are familiar and they've been around for a while. And the building blocks of batteries go back a couple of centuries. And so these have not always been consciously devices in which we're using nanomaterials. But we'll talk today about how nanomaterials are enabling better energy densities inside batteries. To do that, to talk about how nanomaterials are helping us, we need to talk just a little bit about the basic principles of a battery. In a battery, there are two electrodes, such as in any electrical device or any electrical circuit needs two electrodes to complete the circuit. And in a charged up battery, we have chemical energy stored, typically in the form of some kind of anion. Lithium is a famous example, and of course we're very familiar with lithium-ion batteries. We have energy stored in the form of lithium, all being kind of piled up. We use the word intercalated to mean this anion, this ion, is interpenetrated into this electrode. And graphite is an example of a typical electrode that's traditionally been used to store this energy. The form of playing back that energy and turning it into current involves the ionic flow through what's called an electrolyte of these ions towards the opposite electrode. And then in the case of non-rechargeable batteries, that's it. We've expended the available energy that was, you can think of it as kind of having been uphill, and the energy, the anions flow downhill to release their energy, provide a voltage to a circuit, to a device. In the case of rechargeable batteries, we're able to reverse that reaction and drive them back to be stored at their original electrode. And we can do this back and forth many times. Now, as you know, even rechargeable batteries have finite lifetimes, and the various electrodes that we use to build batteries can be degraded over time after we discharge and recharge them many times. And so it's very important to look at new electrode technologies especially that can enable batteries that have longer usable lifetimes, more charges and discharges. Just thinking back to our periodic table, why is lithium a particularly logical metal, a particularly logical element to be using? Well, lithium is what we call the most electropositive metal available to us in the periodic table. That means that it gives us the opportunity to develop the largest potential, the largest voltage, which is going to translate directly into energy. Now, it's also the lightest metal, the least massive per anion. And as a consequence of that, those two things combined, this large amount of potential that every ion can store, combined with the low mass of each of the ions, means that the density in terms of energy per gram or energy per kilogram can be very high with lithium. So it's an extremely good choice from this point of view. Now, where do the nanomaterials come in? Well, I mentioned that the graphite electrode is where we store the lithium in the traditional lithium-ion batteries. And graphite has a reasonable capacity for storing these ions. It turns out, though, that silicon, so familiar from our discussions of nanoelectronics and also of light guiding, that silicon has another remarkable property on top of all of its attractive electrical properties, and that's that it's extremely good at storing lithium ions. And by good, I mean that it can store a huge density of these ions. In fact, if you look at a picture of the silicon lattice, it's got kind of a crucible right inside the lattice where the silicon crystal is ready to receive a very high density of lithium ions. So this is very appealing. But if you look at this lattice, you will also realize that this lithium ion doesn't penetrate into the lattice without disrupting that lattice, without changing it. In fact, if you were to exploit the full energy capacity for storage of lithium within silicon, which is about 10 times the capacity per unit mass that you can store within graphite, if you were to exploit that full capacity, you'd also expand the volume of the silicon electrode by about 400%. And as a result, if you just do this straightforwardly, if you take a bulk piece of silicon or a non-crystalline piece of silicon like amorphous silicon, what you'll find is you can stuff it full of lithium atoms, you can get an incredible energy density in there, and then after a couple of cycles, it will crumble, it will collapse because of all this expansion and contraction and expansion and contraction. It's like the thermal wear on parts or on parts of your house where it gets cold and hot and cold and hot, and the joints start to wear out. The joints also start to wear out within silicon if we change its volume back and forth too many times. But this is where the opportunity for nano comes in. There's been some really exciting work going on at Stanford that takes advantage of nanomaterials to overcome these limitations, to allow us to exploit the incredible energy density of silicon for the storage of lithium without suffering these challenges related to the volume expansion. The way this works is that the researchers have built these long, very, very skinny nanowires, and so their surfaces are now accessible for lithium-ion intercalation, for the penetration of lithium ions into the silicon. But now the nanowires can expand and contract and expand and contract. Rather than a single bulk solid, which would suffer these catastrophic fractures, these small nanowire diameters enable these silicon-based materials to accommodate without fracture these significant changes in volume. Another great thing about the silicon nanowires is they're functioning now as wires, as electrical wires. And so they're able to directly electrically connect to the metallic collector of current. As a result, we don't have isolated materials which can't be collected electrically or where their electrons aren't efficiently collected. In contrast, we're able to make very good use of every one of the nanowires. All of the silicon is active. There's no islanding effects. And finally, it's a direct path. It's a straight line path. We get a direct connection between the silicon nanowire and the electrodes that we seek to connect it to. Now, looking a little bit further out into the distance, into some conceptually disruptive or transformative techniques to try to build batteries, there's been some very exciting, very creative work that's gone on at MIT in which viruses have been utilized to try to assemble new classes of batteries. And one of the stars of this show, it's been actually an amazing example of teamwork. Part of the team is Angela Belcher, who's distinguished herself over the last decades as somebody who's able to work with viruses and use genetic engineering to create families of viruses that have particular properties that dovetail with materials science, that allow us to use bioentities such as viruses to build materials for us. And she's been collaborating with a researcher, Yetming Chang, who's distinguished himself for a long period in the field of energy storage, in the field of batteries. And they've brought their work together to form a very creative collaboration that's completely breaking all the rules of traditional disciplinary boundaries. You don't traditionally see genetic engineering and viruses combined with the kind of electrical, mechanical, chemical engineering of energy storage. And Angela Belcher herself has this fascinating story. She really distinguished herself a little over a decade ago in understanding how living beings build hard inorganic materials. So the abalone shell is a great example of this. And of course, we've been familiar with the fact that you can get these organic entities, animals and vegetables that, as well as forming soft or malleable materials, which is more what we're familiar with in the biological world, that they can also form hard shells, like the shells on seashells. And Dr. Belcher looked at understanding exactly at a molecular, at a nano level, how this occurred. And what she discovered was the mechanisms by which proteins were being expressed by these organisms that were able to capture out of the sea particular elements, such as metals, that were used to build up, say, calcium carbonate, so capture the calcium component to build these shells up. And then another class of proteins were able to promote the formation of the complementary, let's say, the oxide or the carbonate. And so they were able to build up layer by layer by layer by layer these very hard shells. Essentially, they were utilizing organic materials, biomaterials, proteins, to build hard inorganic materials. And she saw this as a real inspiration for her own work. After she kind of did the science of it. She understood how these biological entities were building these hard, very structured inorganic materials using their proteins. She thought, well, maybe we can exploit this. Maybe we can engineer with this. Now, in order to try to engineer with these things, she needed to have some kind of capability to select. She needed to be able to tailor viruses in a direction that she desired. And the approach that she took here, which is taken from the world of phage display, and the idea is that a virus can have various genetic options injected into it. These various families or classes of viruses can grow up. And then we can use selection approaches to only preserve the ones and then amplify the ones that we desire. Well, what would be a selection algorithm? Say you wanted to build a material that was based on, say, cobalt. Well, you could coat some kind of sieve effectively with cobalt, introduce your various viruses into it, and only those viruses that happen to have a gene that led a protein to be expressed that would strongly bind cobalt would stick to the walls of your sieve, and everything else would fall through. In fact, people refer to this as panning or biopanning, an analogy with panning for gold, where what you're looking for, the viruses that you desire to select in favor of, remain inside your container, and everything else goes out. You then have these viruses stuck to the wall of your container. You elute them, which means you bring them back out into the solution, and then you can amplify them. You can have them reproduce and have families, and as a consequence, you can get more and more of the ones that you desire. And so you run this essentially biological selection and a rapid evolution within the laboratory where you prefer the evolution of certain viruses that have certain functions. People had been using this concept in genetics for a long time, but using it in the context of building up inorganic materials, selecting viruses that could do the work of building, say, a battery for you, this was a very novel concept. So Dr. Belcher and Dr. Chang working together were particularly interested in building cobalt oxide. Cobalt oxide is a very interesting electrode for new battery technologies. It's been found to have particular promise, also enabling the dense and reliable storage of a great deal of energy. And there were really two stages to building a virus that was coated with cobalt oxide nanoparticles and that could then be useful in conduction. So the first was to put these cobalt oxide particles on the surface and the second was to make the material more conductive. So for the first one, the researchers used their selection techniques to find viruses that were particularly prone to attract cobalt and to grow cobalt oxide on their surfaces. And they were able to show using transmission electron microscopy that they could generate viruses that had a very rich coating of cobalt oxide nanoparticles on their surface, and that these particles were very similar to one another, so they were quite consistent in their size. In fact, some of the power of transmission electron microscopy is that it goes beyond just our ability to look in what we call real space, to actually look at the image itself, and we can also focus the electron beam onto individual particles and see how the crystals that the electron beams impinge upon spread the energy out, cause it to diffract. The way in which these diffract gives us a clue as to the composition, to the structure of our crystals. And these researchers were able to show that they had indeed built viruses that were able specifically to grow cobalt oxide single crystals on the surface of their viruses. Now, this was one of the building blocks that they needed. The other building block that they needed was something to make these more conductive. And so the researchers found a way to put an additional peptide, so an additional protein on the surfaces of their viruses, to make a kind of, they called it a bifunctional virus, something that could enable them both to grow the cobalt oxide nanoparticles, which were crucial to the battery function, but also be able to grow gold nanoparticles that led to a dramatic improvement in the conductivity of these devices. And so the viruses, as a result, had these coats that consisted of two classes of particles, one the cobalt oxide, another the gold. And the researchers were able to show that they were able to generate these hybrid or bifunctional viruses that allowed them to achieve their purposes in making a battery in this manner. Now, of course, making a battery is more than just making one wire, which these viruses effectively had become. They needed to put them down onto a substrate. They needed to make a practical device out of them. And they found the conditions under which they were able to coat onto just a flexible piece of plastic, effectively, their viruses. And by managing the charge on the viral particles, they were able to ensure that the virus is assembled into nice, smooth, what are called lamellar structures. So there are these kind of stripy patterns of viruses with their coatings of nanoparticles of cobalt oxide and of gold on top of them. That's a discussion of one very important storage technology and how nanotechnology is enabling us to make better batteries that allow for greater capacity, or in the case of this very intriguing work on viruses, allow us to do the synthesis under very environmentally benign conditions. We consume very small amounts of energy in building the batteries this way. It's a very friendly approach to building storage devices. But another area where there's a real need to build devices with greater performance and also with the kind of flexibility that you can sometimes get by using nanomaterials to make devices is in the area of supercapacitors. And I was mentioning earlier, as I introduced energy storage generally, that supercapacitors are another paradigm in storing energy. Their advantage is that they allow you to store, accept energy very quickly, charge up very quickly, and play back very quickly as well. And it's worth defining just the idea of a capacitor. Capacitors are actually traditionally the domain of electrical engineers. Capacitors are one of the building block circuit elements that allow us to store charge. We usually think in electrical engineering of having two plates separated by an insulator, and on one of the plates we can put a positive charge, and by putting that positive charge there, a negative charge is induced on the opposite plate. As a result, there's an electric field, and we have the potential to then release this charge in the form of a current with the presentation of a voltage in order to then drive a device. So they're storage devices, but not typically in the electrochemical sense that's used in batteries, where we're actually moving lithium anions uphill for storage and subsequent replay. Instead, these are typically based simply on the storage of electrical charges themselves, of electrons. Now, in supercapacitors, the name of the game is to try to achieve the greatest possible energy density while also achieving a very good lifetime. This is one of the great things about supercapacitors, is that a result of not moving more massive ions around and imparting true chemical changes, but instead of principally moving electrons around, we're able to achieve devices that can go through many more cycles. So if you think of something, say an electric vehicle, that needs to happen many, many times, now how many times do you apply the brakes, for example, in your car? If it needs to go through 100,000 or more cycles, then often supercapacitors can supply the solution. Some of the exciting work that happened also at Stanford was figuring out how to make a wearable supercapacitor. In fact, the field of wearable electronics has attracted a lot of people's attention and excitement. The idea would be that as well as perhaps making a flexible solar cell that you could go around wearing, you could also store that energy. You could later use it to charge up a mobile device. In fact, people even think of the devices themselves as being wearable. Of course, there's the emerging wearable electronic glasses that can have cameras and processors embedded in them, any number of things that you can imagine doing. But what we'll need to do this is to have flexible fabrics that are also electronic materials. And the Stanford group under Yi Cui figured out how to build fabrics really right on top of traditional cotton in such a way that they were able to store a great deal of charge in them. The way they did this is they started with a millimeter or two thickness of just a fluffy cotton sheet, and then they dipped it into single-walled nanotube ink. So basically a solution containing many nanotubes, and the nanotubes, instead of being of the multi-walled sort, which are contain rings and rings, kind of a coaxial set of nanotubes, instead they focused on single-walled nanotubes, which have better defined and more straightforward and controllable properties. They dipped their sheet of cotton in a couple of times, dried it at 120 degrees C to remove the water from it, and essentially had a foldable textile that was now a conductor. As well as being a conductor, they were able to synthesize and modify the properties of their single-walled carbon nanotubes, where there's a lot of control over the surface properties, to build two properties into it. First of all, they were able to make it what we call hydrophilic. Hydrophilic means that it's friendly to water, and water likes it. And so water was able to adsorb on these electrodes. That was important because the electrolyte that they were using to make their supercapacitor was water-based. They wanted to keep everything simple, environmentally friendly, not use solvents that people might wonder about whether they should be wearing on their clothes. And so they used a water-based electrolyte, but that meant they needed to convert their carbon nanotubes over to being hydrophilic. They succeeded in doing that, and they also used the structure, the nanostructure, the area of these carbon nanotubes as their means to enhance the capacity of their devices to store charge. They proved the idea that they were able to enhance both the density of storage, but also the lifetime of their devices, their ability to play back charge, play back their devices many, many tens of thousands of cycles, even though they were making an electronic device that was on a piece of cotton, that was on a piece of textile, fabric. We've talked in today's lecture about a few strategies for energy storage and how nanotechnology, through the large area of nanostructures, through the ability to process nanostructures from the solution phase, and through the ability to use biological organisms like viruses now to build inorganic materials, how nanotechnology is giving us new ways to make storage elements that are denser, lighter in weight, or cheaper in cost, or integrated with flexible fabrics. We're going to continue this discussion in the next lecture and talk about additional energy storage strategies, and then more broadly about how we can use nanomaterials to control the flow, the playback of energy, and also how we can use nanotechnology to implement desirable chemical reactions with high efficiency through a process known as catalysis. In the last lecture, we ended on another way to think about storing and replaying energy, which is fuel cells. In this lecture, we'll begin with fuel cells. We'll also use them as a way to enter into the fascinating world of catalysis. You know, catalyst is a word that's very familiar. We use it in the English language all the time, outside of the context of science. What do we mean by it? Well, somebody catalyzes a good dinner party conversation. A brief little toss-off remark, a little comment, leads to an hour's worth of vigorous debate. And that represents a good analogy with how we use the term in science. Just a little injection of something, a surface on which a reaction can occur, a particular shape, a particular angle, a particular availability of electrons can lead to a rush of chemical activity. In fact, the idea in science is that a catalyst is something that fosters a reaction without being consumed in the reaction. And so it can have huge leverage, it can have huge impact. Now, in fuel cells, the role of catalysis is as follows. We have a fuel. Let's take hydrogen as an example. This is a very attractive way to operate a fuel cell. With stored hydrogen and simply using oxygen from the air, we're able to produce H2O, water, a lower energy molecule, and the energy that's extracted in going from the higher energy hydrogen and down to producing with the reaction with oxygen the emission of clean water. We take that energy, we harvest it, we turn it into electrical power. We can use it to run a car or to heat a home. Now, that reaction requires a catalyst. Platinum is an example of a metal that's an extremely effective catalyst, and it's been widely used to make these fuel cells operate. However, you can imagine that cost is first and foremost on the list of concerns about platinum. There's also a phenomenon known as catalyst poisoning, where the platinum can no longer be effective after large numbers of uses. So researchers in nanotechnology are very motivated to find ways either to make better use of the platinum, and so to make it more available. And here the large surfaces of nanomaterials are very helpful and attractive to us. There are also efforts to find new catalysts that are not based on precious metals like platinum, but that can dramatically lower the cost of these materials. And another theme that we'll spend time on today is the idea of using nanomaterials for the efficient storage of things such as hydrogen fuel. You know, you can of course store hydrogen fuel inside a tank. It will be under pressure. There's some concerns about the dangers associated with that, but many people think they can be managed. But nevertheless, you can condense even more hydrogen into a finite space if you can get rid of all the free space, if you can have a large surface area material, such as those we'll talk about in this lecture called zeolites and metal organic frameworks, that are specifically tailored to adsorb these hydrogen molecules, producing large surface areas to which these molecules are attached and available for subsequent replay. The excitement over fuel cells comes from the fact that it does provide a means to play back energy. And so when we use wind energy or solar energy to generate power, we can store it in a chemical format and then efficiently play it back. And when you think of the hydrogen-based fuel cells, what's so appealing is that you can simply use clean and available molecules in the air, and your emissions are water. The other advantage over battery technologies, and of course these are complementary technologies, it's not a question of one or the other, it's a question of where the fuel cells can play the most effective role. But one of the advantages in large-scale storage applications, especially to the fuel cells, comes from the fact that we separate out the fuel from its playback. So the batteries are integrated, but in the case of the fuel cells, we have a separate tank or region or material in which we store the fuel. And then we have a separate device for its playback. And so we can optimize those two components separately from each other. So I tossed around the word catalysis. I described its analogy with the way we use it in common everyday language. What do we have in mind, and why are surfaces so important in the process of catalysis? Well, by this word catalysis, we mean fostering a chemical reaction. And sometimes what we mean is that it can increase the probability or the efficiency or the yield of a reaction. Other times, catalysts make reactions possible that simply wouldn't otherwise occur. And one of the key pieces of vocabulary that we use in catalysis is the idea of a crucible. The concept is that certain molecules, say in a gas phase, can interact with each other, they can collide with each other occasionally. But there are two problems if we let a reaction that needs some very specific interactions, if we let it proceed kind of open loop like that, if we let it proceed without some kind of surface or a tether. One is that the frequency of collisions or of interactions between the first molecule and the second class of molecules making up the reaction, that may be infrequent. It may not occur very often. Now, the other challenge is, even when these two molecules bash into each other, they may not do so at the right angle. If for the reaction to occur, we need a particular alignment of sites, if we need a kind of very careful lock and key interaction, and you need to put the key into the lock at just the right angle and just the right way, that's difficult to do and unlikely to do with two molecules that are just bouncing around and fluctuating at room temperature, like little billiard balls bouncing off of each other. And so, the idea of the crucible in catalysis is that we create a surface which attracts one of the molecules that will participate in the reaction, and further, that it will orient those molecules at just the right angle such that the second molecule that needs to participate in the reaction with it will see a set of bonds, an exposed available bond, a reactive site, maybe an electron that wants to jump ship and participate in the reaction. It will see those very readily. And so it will present in just the optimal angle and orientation the right conditions for creating this reaction, causing it to occur. And so the crucible, just as when we think of a crucible bubbling up with a little reaction within it, this is a crucible now at the molecular length scale, at the nanometer length scale. So what specifically does nanotechnology have to do with this? Because, after all, some of these reactions can be catalyzed simply by planar metal surfaces. They can be an exposed facet, say, of platinum. Can have just the right orientation and spacing of the atoms and just the right reactivity to present an opportunity for molecules to come together, interact, and bounce off. Well, one of the areas in which nanotechnology has a role to play, in which there have been some very exciting recent advances, is in what are called zeolites, which instead of being planar, they present a three-dimensional structure. They present a complex kind of, it's like a crystal, like our silicon crystals, but it's also essentially built out of things that look more like molecules. These templates, these structures, they're on a larger length scale. There can be pores that are 1/2 or 1 or 1.5 nanometers in size. These pores can penetrate long distances in these materials. Often there are rings that make up these pores, and the ring diameter can be controlled by the choice of elements that make up the zeolite, the bonding between these various elements, and how prone they are to form these kinds of tubules. Often, because this is a question of various elements coming together and forming a preferred structure, the synthesis of the zeolites themselves is very clever and very tricky and involves a deep understanding of the affinities that various atoms have for each other. Often getting the temperature just right during the growth of these materials is crucial as well, because one needs to give these materials enough energy to react with one another and form these stable and very structured materials. So where can we take advantage of these three-dimensional nanostructured materials in order to achieve innovations, make new products, make new materials? Well, one of them, rather than being in the area of renewables that we've spent quite a bit of time on in this course, is actually in the area of the cracking of hydrocarbons. So taking crude oil and then producing the kinds of fuels that we actually wish to consume. And you might look at this and say, well, this is not as maybe environmentally appealing as talking about renewable energy technologies. But in fact, first of all, this is actually just an illustration of a chemical reaction that can be controlled and enhanced in its yield through the use of nanostructured materials. And in addition, these kinds of fossil fuels have been used for a long time, and we haven't solved all the problems related to providing renewable energy sources. And so it continues to be important to be cost effective and also to be energy efficient in how we utilize the hydrocarbons that continue to be used in industry and in society. So the role here of the zeolites comes in a couple of forms. What we're trying to do in the case of hydrocarbon cracking is to take what are typically the very long hydrocarbons. Think of diesel, for example, diesel fuel, but even longer, even heavier. And we're trying to break it down into the lighter hydrocarbons that we're more accustomed to using, for example, as petrol in our cars. We want to design our zeolite to give it the size and shape such that the reactions proceed to break these longer molecules down into lighter molecules, maybe 5 or 10 repeat units long, these shorter hydrocarbons, these more volatile hydrocarbons. The way in which the zeolites work is first they provide these surfaces for these reactions, but they also produce what we call a steric hindrance. Whenever we use the word steric effects or steric bulk in nanomaterials or in chemistry, we're referring to the effects of size. So we're referring to the fact that certain molecules will preferentially be able to adsorb inside these tubes that make up the zeolites, or they'll be blocked, or they'll move through them very rapidly because they have a good mobility through the tubes or through the pipes, or they'll be slow in their motion because they see these surfaces and they interact with them a great deal. So some specific examples of the zeolites that are utilized in crude oil cracking include the aluminosilicates. And these combine various aluminum, silicon, and oxygen atoms in order to make those structures, those rings with these very defined sizes. The heavy hydrocarbons are introduced, they're brought into contact with the catalyst, and elevated temperatures are combined to inject the energy that's needed in order for these reactions to occur. And then the catalytic cracking, as it's called, proceeds. In fact, the word catalysis is the word in catalytic converter. Here in each of our cars, the emissions that come out of the primary exhaust from our internal combustion energy are further processed. So we're able to further break down some of the emissions into more environmentally manageable materials. And this idea of purification or selection of molecules, it can also be implemented using these zeolites. We use, I think, a very appealing term here, which is the idea of a molecular sieve. The analogy, of course, being, with a sieve, typically we think of a sieve used in the kitchen as being something with pretty defined openings in it. Let's say 1 millimeter or 2 little squares. And so the water is able to pass through, but the pasta or the peas stay inside the sieve. And so what we achieve in that case is size selection on the millimeter scale. Well, zeolites and their friends are able to achieve size selection and also to some degree chemical selection based on the structure of these materials that are produced. So it's really the size and also the shape of the pores that control access for molecules into the zeolite. And so that's the most direct form of the sieve. But another one that's a little more subtle is about speed. It's about selection based on when things come out the other side of our sieve. So for example, we're able to manage size but also chemical interactions on the inner surfaces of these tubules such that those materials that are smaller or less interactive with the surface are prone to move quickly through, whereas others move more slowly, they're stuck behind. And so in this case, the purification isn't necessarily based just on does it go through or does it not? Is it retained on one side or is it transferred? Instead, we can start a process of purification, drive a solution through one of these molecular sieves, collect the products on the other side, but the stuff that comes out first, say, will be the least interactive or the smallest molecules, and the stuff that comes out at the end will be the larger ones. And that's actually very attractive. We may have different applications or different uses for the different constituents of an impure substance. Say we have a large-scale chemical reaction where we make a large amount of something. Well, we may be interested in all of what's produced, but there may be different people, different customers who may be interested in the small and the medium and the large molecules. And so these kinds of sequential purification, where speed translates into time, translates into composition, can be very effective. Now, these molecular sieve ideas are also used in the experimental laboratory all the time. As you well know, water is something that is widely utilized in our world, including in chemistry, including in biology. Sometimes we want to do our reactions purely within water. Sometimes we want to do chemical reactions where there's no water there at all. Water and metals, for example, have lots of interactions with each other. Sometimes we want to control those interactions and just use, say, an organic solvent that doesn't include any water in order to control our reactions with great control and purity. And so what we can do, because of that strong interaction with metals, also cations, which refers to positively charged ions, is that we can make zeolites that have an abundance of cations inside them, of metal ions. And when we pass the solution through, all of the water molecules will stick to this abundant surface area, highly metal-rich, highly reactive, highly water-attractive surface. And what will pass through will be just the organic solvents that we want. And so it's actually quite a simple thing to do in the chemical lab. If you want to dry out a solvent that's supposed to be dry, but you want to make it even drier and only consist of the organic molecules, you can just toss in some of these zeolites and let them sit there for a little while or agitate a little bit, give them the chance to interact, and this sponge will suck the water out of your reaction. Now, one can do the converse. One can work with these organic solvents. Organic solvents often have impurities of organic molecules of slightly bigger or smaller sizes. Or they consist of molecules of different shapes or different polarities. By polarity, I mean a propensity to be polarized, so for a charge to point towards a complementary charge or not. Whereas many organic molecules we're interested in are very nonpolar. They don't have this inclination to turn around in the presence of an electric field. They don't really see the effects of other charges. Well, we can use very hydrophobic zeolites, which means these materials that are specifically designed to be anti-water. Water is very afraid of them, but they're very interactive with organic molecules. We can use these to separate organic molecules into their different sizes. Essentially, we can do molecular sorting. It's a bit like taking a deck of cards that have been randomly shuffled and being able to put them into their categories, being able to put them into their bins, and then potentially every one of the sets of cards is useful. We can use all of them. So it's really the regularity of these structures. If you like, it's the symmetry of their pores. It's the shape, it's the circularity, it's the fact that we're able to use these known chemical reactions between, say, the aluminum and the silicon and the oxygen in order to form rings of a defined size that allows us to define the chemistry that goes on. We can think of these pores as forming traps, little cages or caves that the molecules can get stuck in. So it's the precision and it's the specificity that we leverage in these molecular sieves. In fact, we're not limited to using sieves on liquids alone. Probably how one would think of it, right? Separating a liquid and a solid is the kind of thing that you do inside a sieve. But really, because it's not just about size, we can even work with extremely small molecules. We can work with, say, water, carbon dioxide, sulfur dioxide. We can work with these kinds of gases as well. And so based on their reactivities, we're able to take input natural gas from a low-grade natural gas stream and retain only what we want. And so remove, extract from it some of the components that we don't want in the ultimate natural gas that we'll sell to people. In fact, in recent years, there's been great progress on this. And one of the attractive things about being able to develop these zeolites and engineer their properties so well is that we're able to desulfurize transportation fuels. So we're able to take the sulfur out, which is often responsible for some of the smell in some of these fuels. And we're able to remove that and do so now at room temperature. That's one of the impressive things about catalysts, is that by making reactions more efficient, often a chemical reaction requires a bit of energy to be introduced in order to proceed. But we can introduce the minimum required amount of energy to enable a reaction to proceed. And so we're able to be more efficient in the ways in which we process molecules, process fuels. One of the really exciting things about what we can now do with these zeolites, with these materials, is that we're able to gain greater selectivity as well through the way in which we impart energy into the reactions. So if you think about adding a little bit of heat to a reaction vessel, you're putting energy into everything contained there. So say it was inside one of these zeolites, you'd be putting it into the matrix, into the zeolite itself, and then every molecule that was participating in the reaction would also get some energy. But it's possible to use molecules that participate in our reactions that are light absorbing and that absorb very specific colors of light. So if we think back to our discussions of monochromatic light, of a single color consisting of a single photon energy, we're able to use laser light to selectively excite only a certain class of molecules inside this reaction. This allows us to drive forward the reactions that we desire by putting the energy, putting the excited electrons onto one of the classes of molecules that's going to participate in the reaction. And then, by embedding it in the zeolite, we have the catalyst, we have the crucible sitting right there for us. And we now start to be able to design both where we put the energy and where we put the molecules. So we start to achieve control via position, size of molecules, shape of molecules, and also the amount of energy that we put in. This is both leading us to be able to create new molecules that we weren't able to build before, but also even when we were able to do some syntheses before, we're able to enhance yields. We're able to produce the desired molecule with a higher probability. That has all sorts of advantages. It means we consume less material in the first place. We consume less energy in the realization of these molecules. There's less waste as a result. So it's a much more efficient process. Even the purification steps at the end become simplified as a result of increasing these synthetic yields. I touched earlier on, in the context of fuel cells, there's the playback. There's the fuel cell, which often, till these days, has used platinum catalysts that help translate the stored fuel into electrical energy. But there's also the matter of storing the fuel. Well, let's take a moment to think about what properties we would desire of a means of, let's say, hydrogen storage. We obviously would like, let's say for an automotive application, we'd love to be able to put this fuel into the smallest volume. We'd like to maximize the density of fuel per volume. But if you're thinking especially for a portable application, we'd also like to be able to maximize the ratio of the amount of fuel stored to the mass of this, because if it's in a portable application, we'll be carrying this mass around with us. So any extra mass associated with the storage mechanism will be kind of a penalty that we pay in the efficiency of our car. On the other hand, there are applications in which we'll just have a stationary storage region. There we may be very focused on keeping the cost of storage down, but especially the energy density per unit mass may not be particularly important because we have a stationary storage site. It's in these kinds of application areas that the so-called metal organic frameworks are particularly attractive. In the metal organic frameworks, metal atoms are bound together using organic molecules. We refer to organic molecules that are particularly prone to bind metal atoms as ligand. We say that they ligate the metal atoms. And so we create this network or this framework in which metal atoms occur at various apices or vertices, and connectivity is achieved, the network effect is achieved through these organic molecules that are particularly inclined to want to bind selectively to the metals. Now, as a consequence of this, we're able to achieve an exceptionally high inner surface area. And the surface area is one where, again, we control the chemical reactivity very nicely. If you like, we've engineered chemically tunable structures, where through the combinations of the metal selected, the organic selected, and then the architecture, the spacing, the periodicity in all directions, we're able to achieve a degree of chemical tunability. And this chemical tunability ends up being very powerful in storing hydrogen molecules on the inner surfaces here. We say that they're free of dead volume. So whereas if you were to have a canister in which you were trying to store a gas such as hydrogen, much of the volume would be occupied by nothingness. That within these metal organic frameworks, we're able to remove the dead volume. We're able to condense these materials as much as possible. Now, you might think if we're using chemical effects to bind the hydrogen molecules onto the inner surfaces of these metal organic frameworks, that they'd be kind of stuck there. They'd be irreversibly stuck. But in fact, we distinguish in this field between the idea of chemisorption and the idea of physisorption. So, in general, across physical chemistry and physics, we use chemisorption to mean that there's actually a binding event, that there is a very strong tether between a molecule and a surface or two molecules with one another. Physisorption, often referred to on a surface, we use to refer to the idea of just sort of a light relaxing of a molecule onto a surface. So the amount of energy associated with that is quite small. The surface is present, it provides a little place of repose for the molecule, but it's not a bond that has a huge amount of energy that we would need to break in order, in this case, to extract our hydrogen fuel from our region of storage. Another way to say that is there's no large activation barrier, no large energy barrier that we need to overcome in order to liberate this hydrogen. You might ask, what are the limits of this? How far can we go? How much hydrogen can we store in here? Can we pack a hydrogen molecule on, atoms that are spaced half a nanometer from each other? Well, the metal organic framework is very compelling, but it can't overcome the basic personality of hydrogen. And there's a particular transition for this gas into the liquid phase, and we can't get beyond that density limit. And so we're not getting beyond the intrinsic limits on the densification of this class of molecules. Instead, we're trying to approach those as closely as possible by utilizing the structuring, the selectivity, the chemical reactivity of these interfaces. What we've discussed broadly in this pair of lectures on energy storage and playback is that by having dexterity at the nanoscale, we have a lot of options. We have a lot of degrees of freedom. We're able to do things like control and maximize the surface area of a material, of a structure, in order to maximize the density of energy that we can store on it. And that concept's very related to catalysis. By orienting certain molecules relative to others, we're able to ensure that when a collision does occur, that it occurs at just the right angle to have the greatest impact or to have a chemical reaction that will yield what we desire. We're able to achieve a selectivity. We're able to engineer the structure of these materials to leverage what we call steric effects, effects that relate to the size of molecules. And as a consequence, when we are able to control the size of pores, we're able to engineer the inputs to the chemical reaction and also the outputs. So ultimately, we're able to engineer the reaction itself towards high yield. High yield means better use of the input materials, better use of energy, and generation of a more pure substance at the output. One of the exciting opportunities in these kinds of catalytic efforts, and that has been partially explored, but there's much more to be done, is in taking advantage further of optical control, bringing energy into these reactions using light, often a very pure color of light, such as that which we could obtain from a laser. What this really is an exploration of many of the most attractive building blocks of the nanoworld, our ability to poise electrons, atoms, molecules, take advantage of their interactions with photons, selectively bring in laser light, like a knife, in order to sever two bonds. This is the kind of control that engineering at the nanometer scale gives us. And what it translates into is better use of materials and better use of energy towards our purposes.